now. And I'll say, guys, good morning. What we are going to start off to do today is we are going to be looking at a presentation that I had from some of these things. So give me a second to get us to that presentation. And then if you guys have any questions, please throw them in the chat so I can see what's going on, because it gets a little bit messy and I want to make sure that you guys can see everything that we need to see. So right now, here is what I want us to do, okay? Let me get chat up. Put that up in the corner here. And then I want us to talk about sort of what we're going to do to prove this stuff. Because guys, when I say we're proving this theorem, here's really what I mean. So when I'm talking about this and I'm saying we're proving the linear pair theorem, essentially a lot of what we're going to be doing is going to be taking some of the things that probably make sense and that we're going to be using later, and we're going to be proving them to be as true as we possibly can. Okay, so if I'm looking at this, linear pair theorem says if we've got a linear pair, which would be these two here, then those two angles are supplementary to each other. So here's what I'd want to ask. So right now, what I find tends to be the most daunting of a task is when you're looking at just a blank sheet of reasons here. And so what I want to ask, based upon the way that this is set up, what do you think the first statement of this is going to be? And I'm going to try to do this in annotation mode. So we're going to see how that's actually going to go. But I'm going to do text. I'm going to type it in here, and we're going to see how that's going to go. So what do you think my first statement is going to be here? Does anybody have an idea? Yeah, 1 and 2 are a linear pair. Now, guys, look, being able to do this with the symbols is going to be difficult for me. So like, as I'm going to go through this, the idea of having this be something that I would be able to put the symbols in is going to be hard. When you guys write them, please write the symbols in. So if I say 1 and 2 are a linear pair, that is absolutely right. Now what I'm going to try to do, if I can, is see if I can get this over. Nope, I can't get this over to have the reasons unless I really stretch it out. So let's see if I can get that going here. So what is my rationale for that? Why would that be something that we know is true based upon this? Yeah, given. In this case, the hypothesis of this is our given statement. If 1 and 2 form a linear pair, 1 and 2 are a linear pair, given information. Okay, now, statement 2. We have to lead from what a linear pair actually means. So can you guys tell me, what does it mean if two things are a linear pair? What does that mean that they are? How does that work? What's going on? Like, what is our definition that we can use for this? Okay, so here's the thing. The 180 part is what we're trying to prove in just a second here. What does a linear pair mean if we're really talking about the definitions in the same way? It actually means if we have a linear pair, it means 1 and 2 share a common side and create opposite rays. Now, opposite rays means a line, so it's not too hard for us to figure this out. But when we're talking about this, this is the definition of a linear pair. Now, question for you. If I have two angles that form opposite rays, what does that mean about their measurements? That's my next question. If we're talking about this being, yeah, it's 180. And so what I'm going to have to do is say that the measure of angle 1 plus the measure of angle 2 equals 180 degrees. And the reason I know this is because, mangle, that looks great. Really, I mean, Halloween's coming up. Mangles are good. Measure of angle 1 plus the measure of angle 2 equal 180. 3, in this case, you can say that linear pairs. Actually, hold on. I'm screwing up for a minute. Hold on. This is going to be 3. So you could say 1 and 2 form a straight line. Oops, dagnabbit. Every time I do this, it's going to be a problem here. I apologize. It's hard to type these and do them at the same time. So this is going to be 3. Definition of opposite raise. Angle 1 plus angle 2 is 180. A line is 180 degrees. Now, question. This should be 4, by the way. Sorry. Okay, right now, everybody, it's about to be something a little bit different. I'm going to take this off because it's killing me a little bit. First, oh my God. All right, you guys got 10 minutes of it. I cannot do that for longer. I'm going to die if I keep this up. I apologize. But right now.
Well, don't die.
No, I'll do my best, but this is a something here. Okay, line is 180 degrees. If I know that they add up to 180 degrees, what can I say about angle 1 and angle 2? Are supplementary. And the reason for this is going to be the definition of supplementary angles. Now, there's one part about this that I'm not 100% happy with, and it's these two things. So rules 2 and 3, when we put them together, this is the true definition of a linear pair, and a straight line and the definition of opposite rays. I think you guys probably could have said just this. You could have said 1 and 2 form a straight line by the definition of a linear pair, and then you could have moved to the rest of this. I just wanted to make sure that you could see how these were going to be here. Add another space where? Where is my space that's killing you? I mean, this part, like right here?
I think just between, or yeah, in front of 5.
I don't know if I can. It won't let me go there. Oh, yeah, I can. I have to go in here, maybe? Right now, we'll just have to let it kill you because there's nothing I can do about it. I'm sorry about that.
And that's on death.
So, apologize. This is the best way I can do for something like this. Okay, so here's what I want. Do me a favor, take a look at this proof and tell me, based upon what we have done here, does this make sense to you with what I am doing? Is that something that like this makes sense from a logical part, from a reasons part, and where things came from?
Yes.
So I've got a yes.
At least to me.
Yes. Throw them out, guys. Who else do we got for yeses? I want to make sure we're in good places. Okay, so here's the thing. I don't know the best way to do this in a distance mode, because what I would tend to do is try to give you guys an opportunity to do a little bit of this yourselves. And so I think I'm going to do this. I'm going to clear this. I'm going to shut off the annotating part, and I'm going to go to the next slide. And I think I got to go through a couple here. Hang on. It's not that one. It's this one. Okay. Is there like a... Okay, this is the one I want to do. Vertical angles theorem. I really kind of dig this one, but it is hard to do this in a way that what I'm going to be looking at is going to be sort of showing you what to do as we're walking through this. So here's what I want to do for just a second. What I want to do is I'm going to give you a statement, and then I want you to give me a reason, and then I want you to give me what you think the next statement is. So here's what I want us to kind of show. Right now, we're talking about this using the vertical angles theorem, okay? So let's talk this through for a minute. We're saying if we have vertical angles, and that's kind of the place where we're talking about these, where they're opposite each other, and they're two intersecting lines, and they're the two angles opposite each other from those lines. This picture is the way that it's set up. So we want to be able to say if it looks like this, then the measure of angle 1 is equal to the measure of angle 3. Now, here is the thing. Vertical angle theorem tells us that this is the case. So what I want to make sure that you guys are able to do with this then is to supply reasons and go to the next step. It might be hard for us all to write it down, but we're going to sort of get the process as we go through. So as I start with this, and thank you, Matthew, for filling that in for us. I'm going to do an annotation. I'm going to put the text in here. And when I do this, I'm going to move, I think I'm going to move this wide enough that it'll actually be something we could type all the way into. And if you guys can't see it, I do apologize. I'm going to do my best as we're doing this. So our first statement, angles 1 and 2 are, 1 and 3 are vertical angles. That's something that we have here. 1 and 3 are vertical angles. It's a place to start. The other thing that I want to make sure that you can see here that I think is kind of important is that there are a few other things that this picture is going to give us. And so the vertical angles is a good place for us to start. And so I will move this over to the side. And Dominic, I know it kills you that this is a little bit off, and I apologize. I don't know that I'm gonna be able to get the spaces exact, but we're gonna do our best because I'm trying to type this as I go. So in this case, this is gonna be given. Now, tell me something. What else from this picture can you intuit by the way that we're looking at it? Like, what are other pieces of information we get from these two intersecting lines, and maybe how the angles are related to each other that we could in fact use here? 2 and 4 are vertical is absolutely true. The one thing is, because I'm trying to deal with 1 and 3, I'm not going to put those in for a minute. So let's do this for a second. And right now, 2 and 4 being congruent and 1 and 3 being congruent, that's actually what we're trying to prove. What about the other angles as they relate to 1 and 3? So what about 2? What about 4? How do we think about that one? What would we do? And actually, Ian, you're coming up with a really good point here. If we look at this, if I look at 1 and 2, and Joe, you said the same thing with 2 and 3, those are going to be supplementary. What I could probably say right now is that because these are made with intersecting lines, 1 and 2 are a linear pair, and 2 and 3 are also a linear pair. And we know from that last thing we just proved that that would make them supplementary. So let's do this for a minute. I'm going to use this as a place for given information. I'm going to say 1 and 2 are a linear pair. That's going to be LP. And then I'm going to say 2 and 3 are a linear pair as well. And this is also given because we're using this picture as something we can state from this. So we can say given, because it says if this piece of information is true, that's everything we sort of have here. Okay. Generally, you will be given these facts as a part of the picture, but that's sort of where we're going to be talking about it. Now, how do the linear pairs work if they're going to be supplementary? What does that mean? What do we know? Like, what pairs, what things are, hold on, let me ask that question a little differently. Right now, where it said this, that they're linear pairs, do I know that they're supplementary? Have we stated that yet? That's the question. Did we state it here yet is my question. And Caroline, you're right. I haven't stated it. I have to say they're supplementary to create an equation. So what I'm going to say right now is that 1 and 2 are supplementary, comma, 2 and 3 are supplementary. And I know that from the theorem that we just proved. Part 3. All right, there it is. That's the best I can do, though. Sorry. This is the linear pair theorem, which says that if we have linear pairs, then they are supplementary. Now's where it becomes fun, guys. At least I think it's going to be fun. Hold on a second. I've got something that I need to address here. There we go. I'll let this person into the waiting room, or in from the waiting room. Okay, so here's what I want you to do. What does supplementary mean? Where do we go from supplementary? What can I write? 180. Okay. Now, I'm going to do it like this. Measure of 1 plus the measure of 2 is equal to 180. And then I'm going to go measure of 2 plus the measure of 3 is equal to 180. And how do we know that? Angle measures add up to 180 degrees. Angles create opposite rays. That is absolutely true. 4. Definition of linear pair tells us that we have a line, that we have two angles next to each other with a line. Linear pair theorem tells us they're supplementary. How do we go from supplementary? Yes, definition of supplementary angles. That's what tells us that they add to 180 degrees. If they're supplementary, then they're 180 degrees. That is the definition of supplementary angles. Okay, so right now, what we've introduced is an equation. And I want you to look up here with what we're trying to prove. We are trying to prove that the measure of angle 1 is equal to the measure of angle 3. Now we are moving from the realm of working with our theorems and our postulates to put things together, and we're moving to the place of algebra. So how can I manipulate these two equations so that I can eventually make things go away and say that 1 is equal to 3? Because that's what I got to do right now. I got two equations here. What can I do with those equations to make it so I can start to get something that involves angle 1 and angle 3? Substitute is absolutely right. Well, how do I substitute that? That's my question. Because here, I am going to be doing a substitution, but I need to have things equal to something that I can substitute, though. Do I have that up here? Two plus 3 equals 1 plus 4, or 2. Actually, I'm looking here. 2 plus 1 equals 1 plus 4. We're close. They both equal, hold on, Matthew, let me look at yours. 1 plus 2, and then 2 plus 3, since they equal, maybe 360. We could add them all together, but I don't know if that's going to help us. I think if we look at this, what do they both equal? Yeah, Caroline, substitute 180 for the other equation. So if we look, they both equal 180, right? So if I do that, 1 and 2 is going to be the same as 2 and 3 because they're both equal to 180. So measure of 1 plus the measure of 2 is going to equal the measure of 2. I think, Veronica, I figured that was what you were trying to say, but it was hard to read it. And so my brain couldn't quite process what you were looking at. I'm like, that's the noise that I make when the brain doesn't process. I apologize. It'll look better if I put the beard on when I make that noise, but then I won't be able to speak. Okay, so that's, in this case, it's substitution. And we don't have to say more than one step because it was all the things combined for step 4. All right, y'all, here's the big step. Step 6. How do I go from this to get to measure of angle 1 equals measure of angle 3? That's when you take the 2 away. You subtract the measure of angle 2 because it's the same on both sides. So if I subtract that, I could say that the measure of 1 is equal to the measure of 2. And I could say that by what property? What tells me that that's going to be true? It's so hard to get this over here. Oh, you're right. God dang it. I got to go over there and move it again. This makes me want to die. Dominic, it's true, but you have to tell me the reason why this would be 3 then. Why does 1 equal 3? What did we do? Yep, subtraction property of equality. Correct. Subtraction property of equality is what got us there. Now, have we proven the thing that we're trying to prove? If we look, this is what we're trying to get to. Measure of angle 1 equals a measure of angle 3. We got that. We should be fine. Now, here's the other thing that I want to make sure that we can do right now. I'm going to take another step here. I'll say step 7. This is an add-on. This is not something we had to do. If I said 1 is congruent to 3, what would be my reasoning for that? To say that if I have vertical angles, then they have to be congruent? What would be my rationale for why I could say that based upon what I just did? Definition of congruence. Yeah, that's right. Definition of congruence or definition of congruent angles is what I would be talking about here. And not because that's how it works. Definition of congruent angles is the gong? Yes. Definition of gong angles. Congruent angles is what we're talking about there. Because if we're going to be going from the measures of the angles, we can go to congruence as well. The thing that I like about our vertical angles theorem is that we can, if we need to use measures, we can go from this to say that these two measures are equal to each other, or we can go from this shape right here to say that the two angles are congruent to each other. Now, that is a theorem that we gave you on like the first day we talked about vertical angles in the first place. But this is now a proof of what that is, and that takes us through everything that we needed to do to see where it came from. And actually, what I love about this, and I say that so that you understand, this is something that is actually a pretty important, I guess, building block of the way that we build proofs at the beginning here. What we do is we set two things up to be equal to the same things. So if I add 1 and 2, I get 180. If I add 2 and 3, I get 180. And that's completely and totally a move that we're going to be using a ton, whether or not it's set up with 180 degrees or angles that are actually have a part that's overlapping. It is a way of being able to do this and then use the property of subtraction to take something that they have in common off. It gets used a ton in proof. And so this is the reason why I wanted to make sure that you could see this. And as of right now, I am recording this so you guys can go back and look at it again. But did this proof make sense to you in terms of how we put it together, where things came from, and how it related to the picture in the first place? Let me know, did this make sense? I'm also looking at my time up here. Got a kinda, which is fine. Kinda is a good place for us to be. Kind of yes is good. That takes us to a place of saying at least you can see where this is, and it's a place for us to say, if you were to see it, you'd say, well, I think I kind of know what's going on. And I understand doing it as smoothly on your own is not something we're going to be able to do necessarily great, but it is something that I want us to try. Let's do this. Let me clear this out. Okay, it's all going to be gone. Y'all ready? And bye-bye. Now, I'm going to move to the next slide, I think. That's we already did that. Algebraic proof we've done. All right, proofs with segments. This I'll call this like an old chestnut here. This is something you're going to use kind of a lot. So I want you guys to tell me what to write. And so this is going to be kind of like, we'll call this a group proof because, you know, we're all going to be doing it at the same time. Move this guy over here and you guys tell me what to write. Boom. Okay. Starting it off. What do I do? What's the first thing I have to write? M is the midpoint. Good enough. M is midpoint of
Given.
And that is absolutely given. God, look at all the space here. Okay. I can't, when I do tab, it kicks me to something else. I would have tried to do that. I was using tab earlier and it was not working for me. And I think that's the right idea. And that's how I would have done it, but it doesn't let me play that way. Okay. What does the midpoint tell us? And I know it's AB. So let me get that up here and write it the right way. Okay. What does a midpoint mean?
It means it's like in the middle of A and B.
True, but in the middle, exactly.
Okay.
And so that's the place where I want to make sure we can do this. In fact, Matthew, you gave me a good and important thing. AM plus, not AB, you mean MB equals AB. That right there is the property of the segment addition postulate. Caroline, your idea of AM equaling MB, that is actually the thing that the midpoint tells us, is that not just that M is in the middle, because Matthew, your statement of AM plus MB equals AB, that's just the segment addition postulate. But the fact that it's a midpoint means that the two sides are equal. So we have to state that AM is equal to MB based upon the fact that it's the midpoint. But I really like what Matthew put there because we're going to need some kind of an equation here. All right, so it'll be 2, definition, midpoint. Okay, so for 3, let me put what Matthew did up there, and I'm going to do the edit because I know it's hard to type this stuff, trust me. AM plus MB is equal to AB. And the reason we're going to want to do this is because we have to introduce the idea of AB here. And what is my reasoning for that again? Why is that true? Segment addition postulate. Okay, segment addition postulate. Now, here's the part about this that's important, and I want us to kind of think about this in a general sense. When we have something that we have two things equal to each other like this, that generally gives us something we're going to substitute someplace in an equation, okay? Then if we can create an equation that has more than one thing in it, normally it's going to be angle addition postulate, segment addition postulate, supplementary angles, complementary angles, like definition of that. You're going to create something that leads us to having an equation to substitute in. And in this case, we've got a really solid equation to substitute in. Now, let's look at what we're trying to prove here. We want to show that AB is 2 times AM. So right now, I need to substitute, and right now I've got MB for AM, and I do need to replace those. I need them both in terms of AM. So if I do that, I'm going to need 2 AMs here. AM plus AM is equal to AB. And the reason is going to be that substitute thing in there. That's absolutely right, because I can interchange them. And in fact, we could go back in here and say that 2MB is equal to AB as well. But in this case, this is just substitution. and we did steps 2 and 3 for that substitution. Now, what can I say? Two AM is equal to AB. That's right. And this is one that you can say simplify, you can say substitute, you can say combine like terms, you can say whatever it's going to be able to explain what you did here. I'm actually just going to write combine like terms because that's what we did. Wow, I'm not going to write it well though, because I forgot an M there. So combine, that's something a little different. Combine like terms, but you could use substitution, you could use simplify. You're explaining what you did there. Have we completed our proof? Now, I'm going to tell you, if you did this, I would give you 100%. This is absolutely correct. But I want you to look at something here. And this is the I hate you part of the proof. AB is on the left-hand side. 2AM is on the right-hand side. And because of that, if we want to be really meticulous, we need to flip them, which is a pain in the ass, but still something we have to do if we're going to do this the right way. So here's what I would say. If you stopped at step 5, I would give you 100% because you did the part of the proof that was important. This last part is that last thing that they go, oh, well, you didn't really do it correctly because you don't have the order correctly. Do you guys remember what says I can flip around an equal sign? Transitive isn't that? Symmetric is the thingy. That's right. Symmetric property of equality. Now, guys, it's totally fine if you don't remember it. It is esoteric at best to be able to say you'd be able to pull all of these out. But I do want to show you that step to say, if you stopped here, I'm good to go. This step is the fine last step. But when you get to that other part, if you want to get to the end of it, that is going to give you what you're going to need. Now, everybody okay with this one? Did that seem to make more sense or feel a little bit better about what we put things into for a practice set? Got a couple yeses. I'm going to tell you something weird that is happening right here around me. I can hear the wind blowing outside, and it sounds like somebody going, woo, which is messing me up from down here. So I'm just letting you guys know there's a ghost in my house. Okay, so here's what I want to do. I'm going to stop sharing for a minute and tell you kind of what I'd like for you to do tonight. Okay, what I really want for you guys to do this evening is go back to that assignment that I gave last week through all of what you had for the class. Okay, R2, 1 minute left. And what I mean by that is the problems that we had, you had to do problems 9 and 10, and that's something I would like to see, and we can talk a little bit about 10. But what I want to make sure that you do is you get more of this practice. Try creating these on your own and see in the back of the book if you are getting the right things by doing the odd ones. I want to be able to come in tomorrow. We're going to talk about a new way of developing a proof and a new way of representing a proof. It's called flowchart proofs. And I like them quite a bit, but it's also something where it's a little bit less concrete. The nice thing about the 2 columns is you got, here are your statements, here are your reasons, they match up, we're in good shape. So I'm going to show you this new method just so you have a way of doing it. But the thing that I'm really interested in you doing is just understanding if you can create these arguments and they make sense from point A to point Z. So try doing that tonight. Go back and do more of that homework and do it on your own. Make sure that you're not just looking at the back to see what the answers are. Once you're done with that, then I will know sort of where you are and you can ask really good questions tomorrow saying, hey, man, can you go through problem number 15? Because it made no sense to me. And then we can kind of talk about that before we lead into the rest of it. Does anybody have any general questions before I send you on your merry way? Okay, what I'm going to do just for funsies is I'm going to put the wig on right before you go so that you could see the end of it and you could say, there we go. That's what it would look like, guys. Everybody have a great day.
Bye.
Bye, everybody.
Have a good Halloween.
You got it. You too.